After discussing access control lists and capabilities, we can now move to a different topic, that of authentication. Simply put, authentication is needed to be sure to the extent possible about who the user is before enforcing a certain policy. This is because, as we saw, policies are user-specific. There are different ways for a user to prove he, she is who he, she says. One option can be for the user to show that he, she knows something, like a password. Another to prove that he, she has something, or to prove that he, she is someone. These methods can, of course, be used not only in isolation, but also combined. If we focus on passwords, which are the solution that is commonly adopted, we can agree on the fact that the following are all bad ideas. You can have a look at this by yourself. A prominent example of why these are all bad ideas is the Stuxnet attack. You can search for it and we'll see how something critical as the Iranian nuclear program has been affected by one of these bad ideas. Once agreed that storing directly the password associated with each user is not a good idea, we can look at how authentication works in Unix. A simple form of authentication, which is not adopted because it is not secure enough, is to store the result obtained when encrypting a fixed block of data with a user password rather than storing the password itself. As we mentioned before, if we have a cryptographically secure one-way function, f, it means that from x, we can compute y as f of x, but from y, it is infeasible to find out x, which will be the password in this case. Notice that in this case, it is nonetheless possible to exploit dictionary attacks. Simply put, to try all common passwords, combination of words, until one matches the encrypted set of characters. Notice that if a match is found, all users having the same encryption result also have the same password. A variation to make Unix authentication more secure is that of using an additional n-bit salt, a random prefix of n bits for each user password. Assuming that the value is indeed random and cannot be found out by the attacker, this implies that each word in the dictionary should be tested with 2 power n prefixes, which for large enough n values becomes infeasible. A different alternative is to use one-time passwords. In this case, an interesting example is that of one-way hash chain functions. Supposing you have at your disposition a cryptographically secure one-way function, here simply called a hash function, for which the input and the output have the same length, and also supposing you want to use up to n one-time passwords, you can compute the first password, P1, applying the function n times, as shown in the slide. P2 can be computed applying the function n-1 times, and in general, the ith password can be computed applying the function over the i+1 function. That is, if you want to check the password i+1 is correct, you can check that its hash equals password I. But remember, you cannot find password i+1 from password I. In this case, the server can store P0 and value 1. When the user wants to connect, the server requests password 1, and to check if it is correct, it hashes it and compares it with the local one. If they are the same, then the server can increase its value to 2. It means next time it will ask the user to give password 2 and update its local password value to P1. And this, of course, can be repeated up to n times. As I mentioned before, there are several ways in which authentication can be performed. An alternative to passwords is that of challenge response authentication. A simple way to implement this is to choose as the secret to share the answer to a certain question, an answer that is known by the user but not by anyone else. This, of course, still requires the server-side storing to be secure. The user might also choose a certain algorithm and provide the output of such algorithm to the input provided by the server. In this case, the algorithm cannot be trivial, otherwise the attacker can learn it easily. Finally, a way to go is also for the server and user to share an initial password K, and for both to compute a certain function f over K and the value R shared by the server. If f is a complex function and the user server have enough computational power to run it, and both K and R are large enough, it might be infeasible for the attacker to recover K, even if f is known. Other alternatives include authentication using physical objects, such as smart card and biometrics. In the case of biometrics, an important aspect to account for is variability, to have enough distance in the features between users while allowing some distance even for the same user. Our face does not look always the same, to make a simple example. Of course, another important aspect is to realize many techniques can be used at the same time. If we focus on cards, we can distinguish at least 3 types. Magnetic stripe cards that contain read-only values, password for instance, chip cards that contain values that can be updated, and smart cards that also mount a small CPU and are also capable of participating in the check for authentication. For instance, when using challenge response authentication, or by having the cards computing a small encrypted message that could be helpful when buying something and having no connectivity, and then giving such token to the seller, who can give it later on to the bank to claim the money.